Hello everyone and welcome to my video presentation. In this video, I will share the details about my research project on low-power design of ultra-wideband PLL using Cmos technology. In this presentation video, I will start by outlining my objectives and the scopes of my work. Then I will address the key challenges faced throughout the research process and the timeline that guided my progress. Following that, I will share about fundamentals of ultra-wideband (UWB) technology and phase-locked loop (PLL) system, including with an in-depth explanation of the particular PLL design implemented in this research. Now, let's move on to the core objectives of this research. Our aim was to design a phase-locked loop (PLL) system using complementary metal oxide semiconductor (Cmos) technology. Second, to optimize the PLL system for ultra-wideband (UWB) frequency operation, specifically targeting a balance high-frequency performance and low-power consumption, and third, to evaluate the performance and functionality of the complete PLL system through simulation and analysis methods. To achieve our objectives, this project was carefully defined within the following scopes. First, the PLL system is designed using 130 nanometers Cmos technology with the design and verification supported by Mentor Graphic Electronic Design Automation (EDA) tools. Next, the design targets operations across a wide frequency range from 3.1 GHz to 10.6 GHz while maintaining low power consumption, specifically within the range of 2 microwatts to 10 milliwatts using a supply voltage of 1.2 volts. And lastly, the performance and functionality of each PLL sub-block, such as the phase frequency detector (PFD), charge pump (CP), loop filter (LF), and voltage-controlled oscillator (VCO), are analyzed and verified in terms of power consumption and maximum output frequency. During the design phase, our primary focus was on a critical challenge, which is to design a PLL system that can obtain high operating frequency with minimum power consumption. By overcome this hurdle allows our research to contribute to the advancement of energy-efficient, high-performance solutions that are suitable for integration into the next generation of UWB applications and devices. Let's now outline the key steps in our research timeline, which systematically guided the design of this PLL system. 1. Information gathering. Before any design work began, I thoroughly researched UWB technology and PLL systems, including a deep dive into each of the critical sub-blocks. 2. Technique selection. Next, I focused on identifying and verifying the most effective techniques to achieve both low power consumption and high frequency performance. 3. Design and integration. Once our techniques were set, it was time to bring the system to life by designing the schematics and layouts for every individual PLL subblock, before combining them into the complete PLL system. 4. Verification and analysis. The final crucial step involved extensive simulation and analysis to prove that our PLL system is indeed suitable for UWB frequencies and successfully meets all the project's objectives and scopes. For those unfamiliar, UWB, or ultra-wideband technology, is a cutting-edge wireless communication method. Unlike traditional systems, UWB transmits very short pulses across a wide frequency spectrum. This innovative approach has garnered significant attention in the electronics industry, becoming a truly hot topic. The appeal of UWB stems from its ability to provide high-speed wireless connectivity with inherent simplicity and versatility. This makes it ideal for diverse applications such as smart home automation, advanced security infrastructures, and accurate indoor positioning. With an operational range from 3.1 GHz to 10.6 GHz, UWB offers distinct advantages over conventional narrow-band systems, particularly concerning power consumption and spectrum efficiency. Its low power requirement for short-range data transfer, combined with its non-interfering nature with other wireless protocols, highlights its superior performance. A phase-locked loop, or PLL, is essentially a sophisticated feedback control system. Its fundamental purpose is to synchronize a generated clock signal with a specific reference. You can imagine it as an automatic tuning system for frequencies. To understand how it works, let's look at the block diagram of a typical PLL system. It's composed of three main building blocks. The first block, phase frequency detector, or PFD. This crucial component takes two input clock signals, our reference clock and the VCO feedback clock. Based on their phase difference, it generates UP and down output signals, which act as instructions for the next stage. The second block is the charge pump, CP, and loop filter, LF. The PFD's signals then move to the charge pump, which precisely injects or removes current pulses from the loop filter. The loop filter then smooths these pulses, converting them into a stable control voltage. And the last block is the voltage-controlled oscillator, or VCO. This control voltage is the key. It directly adjusts the VCO, causing it to oscillate at exactly the desired frequency. The beauty of the PLL is its closed-loop nature. The VCO's output is constantly fed back to the PFD, creating a continuous cycle. Through this rapid, iterative comparison and adjustment process, the PLL locks on to the desired frequency. This makes PLLs incredibly versatile for applications like synthesizing new frequencies or precisely recovering clock signals. Now, let's dive into the heart of our phase frequency detector, its transistor-level schematic of our high-speed phase frequency detector, or HSPFD. This crucial component is implemented using 130 nanometer Cmos technology. As you can see in the diagram, the HSPFD takes two input clock signals, clock ref, which is our stable external reference, and clock VCO, the feedback signal from the voltage-controlled oscillator. It then generates two output signals, up and down. The core logic, arranged with numerous PMOS and NMOS transistors, labeled M1 to M18, forms two D flip-flops, a pair of inverters, and two NAND gates. This design allows the HSPFD to precisely detect phase differences between the input clocks and generate the corresponding output pulses. Specifically, the top section of the circuit is responsible for generating the up signal, triggered by clock ref, while the bottom section handles the down signal, driven by clock VCO. Let's observe what happens when our PLL has successfully achieved lock, as shown in this figure. In this ideal state, the reference clock and the VCO clock are almost perfectly aligned, indicating a complete phase lock where their frequencies and phases are matched. Consequently, both the up and down signals show very narrow, brief pulses, or even minimal activity. Ideally, in a perfect lock condition, both would be completely inactive, meaning zero width pulses. This minimal up-down activity is absolutely crucial for maintaining a stable and low jitter output clock from our PLL. Now, let's look at what happens in our HSPFD when the reference clock is ahead of the VCO clock. As designed, the PFD responds by generating a series of positive pulses on the up output. You'll see these up pulses appear every time the reference clock's rising edge occurs before the VCO clock's rising edge. Crucially, the pulse width is directly proportional to this phase difference. Simultaneously, the down output remains completely inactive, confirming the circuit correctly identifies that the reference clock is leading. Finally, let's examine the VCO clock leading condition. In this figure, you'll see the PFD correctly responding by asserting positive pulses on the down output. The duration of these down pulses is directly proportional to the phase lead of clock VCO over clock reference. Conversely, the UP output remains completely inactive, confirming the PFD accurately identifies the VCO clock as leading. Now, let's move to the layout of our HSPFD. As you can see, this compact design occupies 700.399 micrometers square, measuring approximately 30.34 micrometers times 23.085 micrometers. Next up are the charge pump and loop filter, the second critical subblock of our PLL system. This diagram shows the transistor-level schematic of the charge pump. Its primary role is to convert the up and down output signals from the PFD into an analog current. This current then interacts directly with the loop filter, charging or discharging it to produce the essential control voltage for the VCO. The circuit employs a combination of current mirrors and switching PMOS and NMOS transistors. Essentially, it operates with two main current paths, a charging path controlled by the UP signal and a discharging path controlled by the down signal. Next up, let's explore the loop filter, the second crucial part of this sub-block. This diagram shows our passive loop filter, LF, design. Its vital role is to smooth out those current pulses from the charge pump into a smooth, stable analog control voltage for the VCO. This filter consists of three key passive components, R1, which is a high-value P+ poly resistor, and two capacitors, C1 and C2, implemented as multi-finger capacitors. In this architecture, C2 functions as the dominant pole, directly integrating the differential charge pump current to establish the primary voltage change essential for frequency lock. The series combination of C1 and R1 introduces a strategically placed zero into the loop filter's transfer function. This zero is fundamental to enhancing the PLL's phase margin, thereby ensuring superior stability and transient response, particularly during frequency acquisition. R1 also critically contributes to defining the loop's bandwidth and damping factor. The precise component values, R1, C1, C2, were chosen following rigorous analysis, targeting specific PLL bandwidth and damping factor, and optimizing for key performance indicators such as minimal phase noise, reduced reference spurs, and efficient lock time. This figure illustrates the schematic of our charge pump, CP, integrated with the passive RC loop filter, LF, shown here in a test bench configuration. The block labeled conventional CP represents the charge pump circuit we discussed earlier, receiving its up and down pulses directly from the PFD. The filter, as you recall, consists of a series resistor R1 and R2 capacitors, C1 and C2. The resulting output from this integrated CP-LF stage, labeled out, on the right, is the essential control voltage for the VCO. This voltage completes the PLL feedback loop, enabling the system's synchronization. Let's continue by examining the waveform results from our charge pump and loop filter test bench analysis. This figure clearly illustrates the charging characteristic of the charge pump when it's actively connected to the loop filter. Similar to our standalone charge pump simulation, we've applied a series of up pulses while keeping the down pulses inactive. However, you'll notice a crucial difference at the out node. The voltage now rises in a significantly smoother and more continuous manner. This is a direct contrast to the stepped or ramp-like increase we saw without the loop filter. This smooth ramp is precisely because of the loop filter's low-pass filtering action, which integrates those discrete current pulses from the charge pump into a stable analog control voltage. Now, let's look at the discharging waveform from our CP-LF analysis. This figure illustrates the discharging characteristic of the charge pump when integrated with the loop filter. In this scenario, we've applied down pulses to the charge pump input, while keeping the up input inactive. Similar to the charging case, you'll observe that the output voltage now exhibits a remarkably smooth and continuous decrease. The loop filter effectively filters out the discrete steps that would be present without it. This smooth discharge, resulting from the loop filter's current integration, is crucial for ensuring the control voltage applied to the VCO decreases gradually and steadily, facilitating a smooth transition towards the desired lower frequency. Let's now turn our attention to the layout of our integrated charge pump and loop filter. As you can see, the charge pump layout is positioned at the top. Directly below it, that large blue rectangular structure represents capacitors C1 and C2 of our loop filter. And just beneath the capacitors, you'll find the HRP resistor layout. This overall layout design occupies approximately 0.01383750415 micrometers square, measuring around 140.39 micrometers times 98.635 micrometers. This relatively large area consumption is primarily due to the size requirements of the loop filter's passive components. Let's now explore the last key component, the voltage-controlled ring oscillator, or VCRO. Looking at this figure, you'll see its transistor-level schematic. This oscillator is absolutely central to our PLL's operation, as it brilliantly converts the analog control voltage it receives from the loop filter into our desired output frequency. We've implemented this VCRO as a three-stage ring oscillator. This design fundamentally involves an odd number of inverting stages looped back on themselves. The propagation delay through each individual stage collectively dictates the overall oscillation frequency of our VCRO. This figure presents the simulation waveform of our VCRO. The in signal serves as the DC control voltage, while the out signal represents the oscillating clock output. After a short initial settling period, you'll observe that the output signal, out, achieves a near 0-degree phase difference relative to the input signal, in. The precise alignment of their peaks confirms an in-phase or synchronized relationship. This demonstrated ability to produce a phase-aligned output is a fundamental characteristic, making this circuit vital for high-performance clock generation and synchronization applications. Moving to the VCRO layout, as you can see, this is our most compact design compared to the other two sub-blocks. It occupies just 210.044625 micrometers square, measuring approximately 16.905 micrometers times 12.425 micrometers. After designing the schematic and layout for each sub-block, it's time to bring them all together. This diagram illustrates the complete PLL system in a test bench configuration, showing the crucial interconnections of its four fundamental building blocks: the phase frequency detector, PFD, the charge pump, CP, the passive RC loop filter, LF, and the voltage-controlled ring oscillator, VCRO. This test bench operates exactly as we outlined in the initial PLL block diagram. This figure provides compelling visual confirmation of our PLL's functional operation and stability. Observe the top two waveforms, clock ref, our stable input, and clock VCO, the output from our voltage-controlled ring oscillator. Initially, the clock VCO is clearly out of sync. But watch closely as the PLL's intelligent feedback loop engages. The clock VCO dynamically pulls in, gradually aligning with, and eventually locking onto the clock ref frequency. This is our PLL achieving synchronization. Now, let's look at the up and down pulses from the phase frequency detector. Before lock, you'll see them wide and frequent, reflecting large errors. But as the PLL approaches its locked state, these pulses become incredibly narrow and sparse, a precise indication that phase and frequency errors have been minimized. Finally, the bottom waveform, in, is our crucial control voltage for the VCO, smoothed by the loop filter. During acquisition, this voltage steadily ramps, steering the VCO towards the target. Critically, once locked, the in voltage settles to a stable DC level, ensuring the VCO maintains that exact frequency. The clean, smooth nature of this in voltage is a testament to the excellent filtering provided by our loop filter. In essence, this simulation comprehensively validates our PLL design. It undeniably demonstrates its capability to acquire and robustly maintain frequency and phase lock, a core requirement for its integration into UWB applications. This table summarizes the key performance metrics of our PLL system from both transient and DC analysis. Looking at our TRAN analysis, you can see the CL-CREF operating at 3.1 GHz and our locked CL-KVCO at 7.0577 GHz, demonstrating successful frequency synthesis. Importantly, the total power dissipation for the entire PLL system, as shown in our DC analysis, is a low 7.0679 milliwatts, aligning well with our low-power design objectives, and this low-power figure, combined with the high operating frequency, is a testament to the success of our low-power design methodology for UWB applications. Let's now visualize the complete picture. This figure showcases the top-level physical layout of our entire phase-locked loop. Here, you can see how all the pieces come together. The PFD, charge pump, loop filter, and VCO blocks are combined and complete with the essential top-level routing for power and signal connections. The total area of this integrated design is 0.0138620.549 square micrometers, with approximate dimensions of 140.29 micrometers times 98.81 micrometers. So, to wrap things up, I'm pleased to say that this research project has successfully met all its objectives and stayed within its defined scopes. That's everything from my end. I truly appreciate you taking the time to watch and learn about my work today. Thank you.